Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
First of all, thank you all for coming. My name is Dennis Gannon in Microsoft Research in the Extreme Computing Group. And we have two sessions here on cloud computing. And we're starting from the basic architecture through the platform development into programming models, and then finally application-related work. And okay, I think we're ready now. We got all the lunch boxes out of the way. So first speaker I want to introduce is Dilip Bhandekar, he's a distinguished engineer, so we're very fortunate to have him here. He's a very busy guy. He's responsible for our server hardware architecture and standards. We have an organization at Microsoft called Global Foundation Services, which manages and builds and designs our massive data centers. Dilip is currently the chief architect responsible for the technology roadmap for this. Dilip has got like a whole pile of patents, and he's published many papers, so he's well accustomed to academic organizations. Previously, he was at Intel and Digital. He got his MS and PhD at Carnegie Mellon, and I know we have Carnegie Mellon folks around here, so here's one of your own. And I'm going to let him go ahead and get started.
Thanks, Dennis. How many of you have, by show of hands, been inside a data center? Not a computer room. Okay, good. Then I won't be showing you stuff that you've seen. That's good. So I'm going to talk about sort of what is important when we think about data centers and how we think about servers and data centers. At the end of the day, you'll walk out of here saying performance per watt per dollar. So I want everybody to chant that as you leave the room today. A little bit of my background, Dennis talked about it. I got my bachelor's degree from IIT Bombay. Any IIT Bombay graduates here? No, I'm the only, oh, one, good, thank you. So I got my PhD from Carnegie Mellon, then worked at Texas Instruments, Digital, and then Intel. And about 3 years ago, I crossed that Golden Gate Bridge from California, came up to Washington State. And it was more than just a physical crossing of the bridge. I went from being an architect, somebody who went and told people what they needed to buy, to a role in which I decide how Microsoft gets to spend their money. And I have a very different perspective when the money is coming out of my wallet than I had when the money was going into my wallet. So with that, let's continue. So as Dennis mentioned, we are the internal hosting group that designs the data centers, hosts all of the servers. And here's just a partial list of Microsoft online services that are hosted in our data centers. And there's about 200 more that I don't even know the names of, so if you ask me. And that's sort of like the McDonald's 6 million served. By now, it's probably more than that. That's why the plus is important. But you'll see some familiar names. But just to give you an idea as to the scale at which we operate, clearly we have to keep this thing running 24 hours a day, 7 days a week, every week of the year. But to give you an idea, with Windows Live ID, we have more than 1 million authentications per day, with Bing, more than 2 billion queries per month, and it's growing. Today we launched Bing in Japanese for Japan, so we're pretty excited about that. We're taking away search share quite rapidly, so things are looking up for our search business. Hosted Exchange, where we provide hosted services for end customers, 2 to 4 billion emails a day. Windows Live Messenger, and you can see some pretty large numbers there. So we're operating at a scale that's maybe 1 or 2 other companies in the world operate at. So in order to do that, we have somewhere between 10 and 100, a 2-digit number of data centers, some large, some small. Some of our biggest sites are shown on this map. Our biggest one is in Chicago, which has a capacity of 60 megawatts. And then our first Microsoft design is in a place called Quincy, about 100 miles east. If you go on I-90, you'll see it. Well, you'll see the town of Quincy. You won't see a data center with the, we don't have signs in front of our data centers, obviously, for security reasons. So quite an extensive placement of data centers, and we're doing some pretty cool things in Quincy. It's all hydroelectric power. In San Antonio, we use recycled water. And a typical data center consumes about a million gallons of water every week. So that's an important consideration. In Chicago, where the temperature allows, we have what's called waterside economization, where we turn off the chillers and just let the heat go up into the evaporators on top of the building. In Dublin, Ireland, we use outside air for the cooling. So that helps. Environmentally, it's more efficient and also helps keep our costs down. In addition to that, we also have caching nodes spread around the world where we cache data so you can get faster access to it. So before I came to Microsoft, when I thought about a data center, that's what I thought about, right? Raised floor with lots of racks. But there's more to what a data center is. There's all kinds of other infrastructure things, substations, diesel generators, battery packs, storage for diesel, et cetera. So there's more to a data center than just servers. So if you look at what it costs to build a data center, the typical cost numbers for the industry are somewhere between $10 and $20 million per megawatt. So if you're building a 27 megawatt data center, you can do a quick arithmetic and see that it's a huge investment. But if you look at how the cost is divided up, this is not including the servers. This is just the data center before the first server arrives. A significant chunk, about 3/4 or so, is in the electrical and mechanical. What does that mean? It means all the transformers, the UPSs, the generators, all of the cooling equipment, and all of the piping and all of the wiring that goes into the electrical and mechanical system. So the important thing is to pay attention to that. If you look at land costs, it's only about 2%. So you can go off and buy land way earlier than you need the capacity. The building itself is less than 10%. So what are we trying to do? The place, if you want to reduce your costs, the place you want to focus your energy on is the electrical and mechanical, and I'll show you how we're doing that. So why is power important? If you look at the power cost in the US, it's the average, and depending on where you are, it can be anywhere from 3 or 4 cents up to 20 cents. Average, according to the Department of Energy, is about 10.27 cents, and this is for large industrial customers. And the other thing to remember is there's a metric called the PUE, or the power usage effectiveness. And what that says is we usually look at the power consumed by the servers and the network equipment. But for every watt that's consumed here, the rest of the system coming from the utility down is somewhere between half and another watt. The industry average is more than 1 watt, which says that the PUE, that ratio, is greater than 2. Now, in our data centers, our average annualized is about 1.6 across all of our data centers. Clearly, our newer data centers are much better than that. The older ones are worse than that. So it's really important to look at power. Now, there's more to power. As I mentioned, it costs about $10 to $20 million per megawatt in capital investment to build a data center. And so if you take the total cost of ownership and say you're going to keep your server around for, let's say, 5 years, and I did this with a server I think was about 300 watts or somewhere in that range. So now if you're building, let's say, a 20 megawatt data center, you need to allocate the capital cost, the depreciation on that capital investment, in proportion to the energy being consumed by that particular server. So when you do that, what you end up with is this green piece of the pie, which is about quarter of the cost, which is the depreciation that's allocated to that server. The blue piece here is the actual energy consumption cost of what you pay the electric company for the energy that you consume. And if you look at the the capital expenditure of the server itself, it's slightly less than a half. So just looking at the server doesn't make a lot of sense. So you want to kind of, we focus on trying to reduce all three of these, and as we move in the future, that split will be slightly different, but the total cost per server fully loaded will also be much lower. And of course, your mileage will vary. This is an illustrative example. So what do we do to reduce our costs? Well, I came from a server background, and when I started working with the data center guys, they used to make assumptions about how the servers were going to operate, how cool the air needed to be for the servers, and they would sort of build in some margin saying, oh, if those guys say, they need 250 watts, we don't want things to burn up, so we'll plan on giving them 275. And then we turn around and say, oh, they say that they're going to give us this much, and we built a margin. So now if each of us builds a 10% margin, right there you got a 20% inefficiency. So very quickly we realized that we needed to think about this holistically. Having the most efficient data center without having the most efficient servers doesn't make sense, and vice versa. The PUE is an excellent metric, and it's good to track historically how well you're doing. But blindly looking at PUE doesn't work. For example, in the PUE calculation, the power consumed by the fans in the server are part of the IT load, right? Now, if I have a design in which I remove the fans from the servers, the server power goes down, and my PUE gets worse because the server power went down. So if you blindly apply something like PUE, it doesn't work that well. The other thing we've spent a lot of energy doing is right-sizing our server configurations. And I have a longer paper that I presented at ISPAS 2009 that goes into how we did that. So we analyze all of our workloads and try and figure out, what we really need in our servers. So 3 years ago, when I joined Microsoft, we were buying off-the-shelf servers from different OEMs. We started an effort to customize our servers. So we specified exactly what we needed and had the OEMs build it for us, which gave us 20 to 30% power reduction, 20 to 30% cost reduction without sacrificing performance. And I'll talk some more about that. We also when I was at Intel, I loved the people that would pay top price for the highest frequency processor. Those were my friends. But now that I have to spend the money, the low power processors are much more efficient from a performance per watt per dollar perspective. And in all of our purchases, we optimize the total solution for the best performance per TCO dollar, not purchase dollar. So let's talk about how we do this. I remember when a certain company, which no longer exists, used to say that the network is the computer. Well, the new slogan we have is the data center is the server. And we focus on, as I mentioned, performance per watt per dollar. Now, the other thing that we do that's different than some of the other people in this business is we don't believe that we either have the knowledge or the resources to do all of this by ourselves. So we form strong partnerships in the industry with our suppliers, the Intels, the AMDs, and a small set of OEMs, component suppliers, people that build memories, disk drives, and network equipment. And we expose to them our detailed requirements and work with them. So if the theory is, if we can explain to them exactly what we need, we have a higher probability of getting what we need instead of them selling us what they want us to buy. And so our end goal then is to provide best-in-class infrastructure for those 200-plus online services that we support. Now, part of our cost reduction strategy is right-sizing the server. What does that mean? Well, in the old days, when you walked into a data center, we bought off-the-shelf stuff. Every single server had a CD-ROM or a DVD-ROM in it. I've never seen anybody in the data center walk up to 10,000 servers and load software from a DVD, right? So we made them take that off. That was simple. Then when we looked at a lot of these platforms, they were designed to serve a set of needs that were pretty wide. So they had lots of PCI slots, lots of memory slots. We knew how much memory we needed. We knew how much I/O expansion we needed. So we had them remove those things, which reduced the board size, gave us higher density, lowered our cost. And also it allowed us to use smaller power supplies, because if you're not going to, typically what happens if you have all of these expansion slots, the power supply is sized for the maximum possible configuration. And now you have a power supply that's 700 watts that's operating at 200 or 250. It's not operating at its most efficient operating point. So those are just some examples. The other thing we did is that we had a feeling that these servers could operate at a much higher temperature. So we had an experiment outside our data center in Tukwila where we took some old servers and put them outside under a tent. And we ran them for about 6 months, and we didn't see any failures. The only problem we had was in the fall when some of the leaves got sucked close to the air intakes. Once we blew that off, we were fine. Then we built one of this air handling unit, and we ran that with our partners in the research group to see how well they performed running completely outside. And after that experimentation, we've sort of now committed to free air cooling wherever possible. The idea is to eliminate chillers. I mean, clearly, another cost reduction strategy is virtualization, and in Windows Azure, virtualization is sort of part of the basic package. We also use power management, power capping to take care of the unusual peaks. Otherwise, you've got to kind of plan your capacity based on peak power demand instead of some sort of average or nominal case. So there's an organization, industry organization called ASHRAE. It's the vendors who build heating and cooling equipment. So obviously they want you to run your servers sort of between 65 and 80 degrees because they provide cooling equipment. Well, we looked at the specifications that the vendors provide, the OEMs, and every single one of them says that the warranty goes from 50 degrees to 95 degrees. So why not use the entire spectrum? So we're telling those vendors that we've read your warranty, we know what it means, we want you to support that full range. And this is what allows us to go to free air cooling. Okay, let's talk about performance. So this is an old example, about a year and a half old, but it conveys the idea. So these are 3 Intel processors that were available at that time. And one was a 50 watt at 2.33 gigahertz, 80 watts at 2.67, and then this go for maximum performance at 120 watts. And here's what I did. I said, let's normalize to this. And this purple piece is performance. And I said, let's be generous and assume that performance scales with frequency, which it never does. But I said, okay, let's just take the sort of most optimistic case. And here, this gives you 7%, that gives you 18%. The next thing I did was looked at system power, not just the processor power. If you just look at the processor power and cost, the results are even more dramatic, but that's kind of unfair. So what I assumed was that the server price before you add the CPUs is about $2,000, and then you add the cost of the processors. For power, I assumed that the total system power is 150 watts plus the CPU power. So when I did that, my performance per watt started going down dramatically, and then performance per watt per dollar, you can see that going for this highest performance processor cuts that in by a factor of 2. So we're strictly focused on 40, 50, and 60 watt processors from either AMD or Intel, and we're pushing them to drive that even lower. In most of our applications, we're not performance constrained, but we're power constrained. Okay, to move on to data centers now. Years ago, when MSN was first launched, Microsoft used to rent space like everybody else in third-party data centers. We'd essentially buy servers 1 or 2 at a time, put them in racks, and then as the business got bigger, about 3 years ago, we built our first Microsoft designed data center, and we started buying things mostly in sort of fully populated racks that allowed us to bring 40 or 80 servers, depending on on what kind of density we got. And then worked our PUE from about 2 down to 1.4 to 1.6. And then about 2 years ago, we had this notion that maybe we can get even more efficient and more agile by moving to containers, where you have about 2,000 servers inside of a shipping container. So we started designing Chicago, and in the container side, we're seeing PUEs of about 1.2. The raised floor is about 1.5. And then I'll spend time talking about our next generation, which will be bringing online later this year, where we're going to free air cooling and driving PUE even further down and going to really a modular design. So this is a picture of the entrance to our Chicago data center. And just to kind of give you some feel for what it takes, during the 18 months that the construction was going on, there were about 3,000 construction workers, 1.5 million man-hours of labor, lots of copper, lots of piping, over $500 million investment, chill water piping. Somebody translated that 707 square feet floor space into either 17 or 19 football fields. And that's American football. I don't know what a soccer field size is. So here's what Chicago looks like. The top floor is your traditional raised floor colo space like any other data center. The bottom floor is essentially parking spots for containers. And what we did when we decided to buy containers was we didn't want to constrain the OEMs to a specific design. So what we told them was the physical space, how wide, how tall, how deep they were allowed to be, the weight restriction, the amount of power they had. These are water cooled, so we told them the temperature of the water and the flow rate and the network connection. Beyond that, we didn't care what they did inside. They could do the servers vertically, horizontally. They could distribute DC inside. Could be 48 volts, 12 volts, could be AC. We didn't care. We told them which processors, we wanted the low power processors, how much memory, what kind of disk drives and how many. And then we essentially said, tell us what it's going to cost us to get, and how many servers could you populate in each of these parking spots. And the ones that gave us the most compute per parking spot at the lowest cost was the ones we went with. So it kind of allowed them to innovate and allowed us to kind of pick the best of breed. So now let me show you a video of one of these containers arriving and being deployed. This whole process takes about 2 or 3 hours. So they come in on a flatbed truck like that. So this was a double stack design where the servers are on the bottom and the electrical and mechanical equipment is on top. So you take it off with those gantry cranes, take the bottom one off, roll it back. Those orange things you see are air skids. You pump air in them, and then it just takes about 4 or 5 people to move 60 to 65,000 pounds. Then you lift the top one up, slide the bottom one back underneath it, and then again, see there's 3 guys here, probably 3 guys on the other side pushing it.
Who did the musical score?
I did. I didn't like the video that the PR people had, so I had to change it. Oh, this is being recorded. Okay, Monica's going to come get me. We have a fire hose-sized water connection. You connect the water in less than 3 hours. So we can actually do 2 of these in a day. Now, once they're connected, then they're ready to be, to test inside, in transit. Sometimes, some of the drives get damaged and so forth. And within days, we can have 2,000 servers up and running. It's pretty cool stuff. So what's next? The next step for us is to get to a modular design. One of the challenges you face is that you don't want to build capacity too early because of the tremendous cost that you have. And you don't want to be too late because if you need the capacity and don't have it, then you lose business. So you have to find the right mix. So what we decided was that we needed to go to a modular approach using pre-manufactured components so we can build out capacity as you need. So our whole goal was to get scalability while reducing our time to market and reducing the overall initial investment. So what you do is there's a certain, you have a much lower initial investment, and then you sort of start adding more cost and capacity as you want to bring in more servers. So for example, some of the mechanical stuff, electrical stuff is also pre-manufactured. So you bring in a container, bring in the transformer and the UPS that's needed to support it. And we believe that we can get a 30 to 50% reduction in the cost of deploying these servers than a traditional race floor data center. So the whole idea behind containers, initially they really were ISO containers that they would buy from the same people that sold to shipping companies, and then they'd cut holes in it where they needed. And then after the first few were built, they found that it was easier to just start with I-beams and sheet metal and build your own to a certain size. There's nothing magical about exactly the ISO dimensions. And the whole thing that makes containers work is not the fact that they're shipping containers, but it's the notion of containment. You're dealing with a well-defined, well-controlled, smaller volume of airspace, and it's easier to control your airflow, et cetera, in that contained model. So learning from that, we decided to move to sort of specifying things where the height can be different, the width can be different. The only thing you've got to be careful about is that these things have to be transported by road. And the Department of Transportation has guidelines on how high the bridges need to be. So if you make it too high, you're going to have a problem getting it to your destination. And some of these containers, depending on who we buy them from, come from over 1,000 miles away. There are also weight restrictions. You've seen these weigh stations. They not only weigh the weight of the container, but also the load on each of the axles. So I was observing a container installation last week, and they had 5 axles on the back part of the trailer, and even that wasn't enough. So let's see. Our whole idea is to use outside air cooling. In some geographies, you can't use outside air cooling 365 days of the year, so you do need to provide some form of secondary air cooling. But we think part of our site selection for data centers is going to look at the temperature and humidity information, and wherever we can, we're going to pick places where we can use free air cooling every day. Now, if you're going to a place like Singapore or my hometown of Bombay, you're stuck. I mean, the humidity is something that you have to accommodate for. Turns out that high temperature is something you can deal with. It's the high humidity that's harder to handle. Okay, so here's another video of the concept of our next generation. And IT-PAC stands for IT pre-assembled components. So here's sort of conceptually how our next generation containers are going to be built. And the one that you see up there was built almost exactly like this. The drawings were entered with a mechanical CAD tool, and then that was transferred into numerical control machines, which cut out all the pieces. And then over the next couple days, 2 people assembled the whole container. So here's the sort of main structure. Needs a control panel. There's the fans on top that create the negative air pressure to draw the air through. The air goes out the back. Bus bars for the electrical connection. There's the servers. This is the picture of a 20-foot design. Lights. Mixing dampers. They're there to mix hot air coming from the back into the front when the temperature gets too cold. The air washers are, if you heard of a swamp cooler, this is exactly what it is. It's an adiabatic cooler where you wet this thing, and as the air flows through, it sort of cools it by 10 to 15 degrees. The outside louvers are also to control the airflow. So when it gets too cold, you want to kind of use more of the recirculated air and less of the outside air. So here's 4 modes of operation. Normal operation, air just comes in, hot air moves out the back. Now watch the temperature, which is the top left. As the temperature starts to rise. If it gets above about 90 degrees is when you turn the evap washers on, so water runs down those, and now outside temperature is 104, but the inlet into the servers is only about 90. At night, if it cools off, you can go back into normal operating mode. Then in the winter, if it gets too cold, you start recirculating the hot air. You sort of close the outside air a little bit, so maybe they're only open 25%. And now outside is 25, but the air going into the servers is about 50 degrees. And then if the humidity gets too low, that's not good either. So now you run the evap washers again just to add some humidity into the air. It's a pretty simple concept. We've built a few of these and are testing it. In fact, there's one unit at the Worldwide Partner Conference in Washington, D.C. Being shown today. Then you just stack them, connect water. And look, the water connection here is a garden hose kind of size and flow rate. It's not the fire hose that you saw in the water-cooled containers. The other thing we pay attention to, as I mentioned, is the server platform itself. My top 3 goals, as my boss tells me, is low cost, low cost, and low cost. Obviously, it has to be reliable too. That goes without saying. The design has to be rack optimized to meet our requirements. And in fact, it has to be container optimized. So the rack piece is just an intermediate step. We try and use common components for all of our server configurations. Clearly, our focus, our largest consumption is for Bing for search and Windows Azure. So we try and optimize our server designs for that. Right sizing to reduce cost, power efficiency. Oh, the other thing I forgot to mention when I talked about right sizing is we also use higher efficiency power supplies. We also use higher efficiency voltage regulators. And we size the voltage regulators to support only the 50-watt processor. The fact that you can plug in a 120-watt processor is irrelevant to me. So since I'm never going to plug that in, I don't need the VRMs to be sized to support 120 watts. So they're more efficient, lower cost, and therefore more energy efficient. So the whole idea then is to get performance per dollar per watt. Now the performance per dollar per watt is a simple way of saying reducing your total cost of ownership. The actual thing is you have to work through the analysis that I showed you, the depreciation, the energy consumption cost, but it's sort of, this is a good first level way of thinking about energy efficiency. Obviously, sustainability is important to us, so you got to kind of pay attention to it on a constant basis. Oh, the other thing I forgot to mention is when you're buying 2,000 servers and they come in a container, there are no shipping crates, there are no cardboard boxes to dispose off, so it helps on that too. The other thing that's important is you have to constantly measure your environment. The temperature in a data center, the power characteristics, your PUE. It's really simple. If you don't measure it, you can't control it. So you have to measure. So we have a lot of instrumentation in our data centers that we measure. If I had my laptop here, I could have pulled up a website and look at the PUE today across all of our data centers. So in conclusion, then, that having a holistic approach to optimize your servers and data centers together is the way to get the most energy efficiency. Platform energy efficiency will always be a top thing we pay attention to. That's not going to go away. Stranding power is expensive. I hadn't talked about stranding power. What that means is if you built a 25 megawatt data center and it's costing you $10 million per megawatt, you want to use every last watt. And you don't want to strand power, which is if you only use 20 megawatts, the other 5 megawatts you paid for the capital investment, you're not getting any return. And if you remember, the building costs were so low. So one of the things that we try and do is is always have more physical space than you need. So you want to run out of power before you run out of space, because if you run out of space and you strand power, it gets very expensive. Using free air cooling and running these servers at high temperature is a great way of reducing our costs. You have to continuously do workload analysis, because if you don't understand your workloads, you're not going to be able to right-size your servers. Total cost of ownership is what we need to focus on, not purchase price, measure and control server parameters. And what I've learned over the last 3 years doing this, and in fact, over the last 33 years that I've been in business, is don't do something just because somebody says that's the way we've always done it. Always question conventional wisdom. And with that, I think you're taking questions at the end, or you want to? Okay. Yeah.
Sustainability. What do you do with these containers after you've used up their lifetime? Is there a refresh on them?
That's a good question. Since our containers are only a year old, we haven't hit that problem yet. So there are several options. We'll see how the technology evolves. And if there's a tech refresh that's more cost effective, then that's what we'll do. In the worst case, we'll have to scrap the containers and send it, it's metal, which is more recyclable than plastic. So worst case scenario, they get recycled at a metal recycling. Best case scenario is that there's some kind of tech refresh that happens.
So you'll have to do the whole dismantling of everything too.
Yes, we'll have to take them out and repeat. There's no undo button. We need an undo button on the installation. But yes, that's an issue that we haven't had to deal with, and something that we're wrestling with. Maybe if you can line up here.
Okay, here's a question. Since the servers are packed in the container,
Yeah.
so how is the maintenance done? I mean, if there is something is burnt out or something.
Okay, the question of maintenance. The containers right now are running software where software has resiliency built into it. So if I have 2,000 servers, the software will continue to run even if, let's say, 1% of the servers are not working. So we're not, and I think this is the sort of the wave of the future for the cloud, that you have to have software that's resilient enough that you can shift the load to another server very quickly. So in this model, what happens is that there's a certain threshold, around 1% or so. So until we hit that threshold, they don't have to be replaced. And so what typically happens is we either wait until that is hit, or once a week somebody goes through and replaces all of the failed servers, and we just remove the entire server. And depending on who's designed, there are some that just kind of snap in. Others you got to kind of remove a couple of power cord and a network cord, and then pull them out, slide a new one in, repair that one, and then that goes into your next spares supply. That's the way to do it. If you're in a mode where these things have to be up and running all the time with, to be replaced within hours, it doesn't work that well. And I think that's the way of the future: more resiliency than high reliability.
Okay. Now that it's been announced that you'll be able to buy Azure in the box, what role do you see these containers playing for customers themselves buying units of this size or a different size?
So maybe Yusuf has a better answer to that. But the Azure appliance model is that the companies that we've named and any additional ones we add are the ones who are going to provide the hardware, and we provide the bits to run on that.
We basically have reference designs for the actual, what the software needs. The respective OEMs, we announced yesterday, HP, Dell, and Fujitsu, will design their own, and we will sell it through them. So they will have opportunities to innovate as they see fit, if you will.
And will some of that experience that you've described feed into those reference designs?
We work closely with a bunch of OEMs, as Dilip mentioned.
Yeah, some of the OEMs on that list are people who've supplied containers to us.
So you spent a lot of your talk talking about modularizing the compute supply. I was wondering, have you guys spent a lot of time thinking about, or is it possible yet to modularize the power distribution in terms of, none of these things seem to have built-in diesel generators or, built-in battery supplies, and so you're still talking about speccing out land and distribution for 27 megawatts, and then laying in container after container. Is there a way forward where we can think about modularizing the power at the same time?
I didn't talk about the other pieces. Yes, the other pieces are also modularized. Like for example, we talk about IT pack, we talk about UPS packs, we talk about transformers. So what you could see is most generators come in about 2.5 megawatt sizes. So let's say if a container is 500 kilowatts, we would bring in a generator for that 2.5, and then it'll be shared across 5 containers. Then when we need to bring in a 6th one, then we bring in another generator. Now one of the challenges in some of this is the lead times for some of this equipment, so you have to kind of pre-order. And even if you look at the generators, it's not the entire generator. There's probably one pump in that darn thing that has a longer lead time. So there are ways in which you can mitigate that and maybe pre-buy with your vendor, say, okay, we'll fund you to keep in inventory the one item that's the longest lead item, and then as we need them, we'll buy the pieces. But yes, the idea is to modularize the rest of the infrastructure too. Didn't quite talk about it.
So this is a follow-on to the previous question, the 2 questions ago. How would you imagine smaller scale data centers, maybe at the university level, benefiting from some of these best practices?
Good question. I mean, the smallest unit that we've played with is about 20 foot, about 200 kilowatts or so. There's a certain minimum size that you need to be at. If you're just buying 3 racks, just putting them in a closet somewhere is probably more cost effective. There's a certain minimum size that you need to start with. My sort of gut feel says that that's somewhere in the 1/4 to 1/2 megawatt.
Well, what's your sweet spot in terms of number of cores per die?
That's a software question. Somewhere we're using 2-socket servers, and right now we're using 6-core processors in there. In the places where we've got Intel, we don't always turn on hyper-threading either, so it's 12 threads. Sometimes, in some cases, we found that when you turn it on, the performance benefit isn't there, or it goes down. I'm looking at Avi because he was a processor designer at Intel, so I have to give him a hard time because I can't give myself a hard time. So anyway, it's 6. We think 8 times 2 is sort of the as high as we can go. Now this is in a monolithic application. Under virtualization, I think that limit can be extended. There it comes down to basically as you add more cores or more threads, and you put more VMs, you're going to need more memory. You're going to need more storage, more network capacity, and so you have to look at that whole thing and decide what the sweet spot is. But I think the sweet spot could move further down in the presence of virtualization than it would in a sort of traditional old style. Just put one OS image without virtualization.
In practice, we find the network to be the issue, to be honest. I mean, we can create more cores nowadays, but the network and the cost per port is the issue.
Yeah. Now, as 10 gig costs come down, that could change.
A few years.
Does anything change if you start running sort of HPC type workloads on the cluster?
Yes and no. I think the HPC guys value performance more, but if they actually did the analysis to see what kind of value they're getting, and basically, if you can distribute your application and you've got the room to have a larger number of servers, then you're much better off having the ones that have the best performance per watt per dollar. Getting 10% more performance at 50% more power and 50% more price, to me, doesn't make a lot of sense. But the financial industry has different metrics, and sometimes they will tell you that turning a trade around in 100 milliseconds before the other guy's scan is worth millions of dollars. So their TCO analysis is completely different. So I'm not saying that this is for everybody, but certainly in the cloud-based services kind of thing, this seems to be the right approach. Again, it depends. Most of our applications don't have cross-server traffic. Now, if you're solving a large problem and sending data across multiple nodes, then the network traffic becomes a bigger issue.
We have time for maybe one or two more here.
So are you looking at any kind of dynamic optimization as workloads vary during the day and power consumption varies during the day, and even spatial optimization within the data center?
We've thought about it, but people get really nervous about sort of playing around with things because it's hard. You can't use history to predict what the load's going to be. And so we're a little nervous about doing that, except for the places where we're not that performance sensitive. And so if you've got a small website, you're running stuff, those can be moved around. But for the things like our search applications, we've kind of hesitated from doing that. So in some places it does make sense.
So some of the companies we work with, they do have patterns on their workload. So
yeah.
E-commerce applications, things like that.
If it's predictable, yeah, you can do that. If you know that you close your books once a month at a certain time, and that's where a cloud service like Azure is really great, right? So if you have a peak load once a month, you can go sign up for a service like Azure, and you get that capacity for the 3 days when you're closing the books, and the rest of the month you kind of say, I don't need that, and that's the way I think people can get some cost reduction.
One more question, and we got another talk to move to.
So just real quick, is there a separate design for a storage container as opposed to a compute container where you'd have much more disk per server or whatnot? And then one actually related to this last question, would it ever be possible or make sense to be able to power cycle these large containers, be able to turn them on and off?
Yeah, clearly you could turn them on and off. What that amounts to is if you completely turn something on, then you have to be willing to put up with the latency of turning it back on, right? Or if you know that your load is predictable, that nobody logs in before 8 o'clock, you turn them on at 7:30 in the morning. As far as storage goes, what happens is the storage configurations are, if you look at the power is much less. So depending on how many drives you have, the overall power per server can be different. The space can be different. So you just have to work through the numbers. And while on some of these sort of low storage content servers, I can get 2,000. Maybe with lots of storage, that number gets cut in half, and the power gets cut by 30% or something like that. So you just have to look at those numbers, and then, like I said, if I have enough space, it's okay for some of the containers to not be at the, let's say my max limit for the container is 400 or 500 kilowatts. If some of them come in at 300, as long as I have enough space to land them, I'm okay.
I think at this point, I want to thank Dilip a lot for coming here and sharing this with us. So thank you.
And I'll be around at the end if you want to catch me during the break.
Great. So we're fortunate to have another distinguished engineer. Yosef Khalidi is here from the Windows Azure team. He's been heavily involved in the architecture of that. Prior to Microsoft, he was also a distinguished engineer at a favorite company of mine called Sun. And we're happy to have him here. And I've got a whole 2 paragraphs, but I'm going to skip it so he can get going.
Thanks, Dennis. So good afternoon, everybody. My name is Yusuf. I'm here to give you a presentation about cloud computing in general, some of the cloud challenges and opportunities going forward. And I'll anchor a discussion with the thing we actually built called Windows Azure. But it's mostly about the challenges going forward versus what we have done so far. Okay? So my whole talk is actually summarized in this one slide. So if you want to leave the room, just listen to me for one slide. Basically, there's a value prop for cloud computing that we sort of all believe in and love and so forth. And I want to preface my comment by saying cloud computing is at the peak of the hype cycle at the moment. So a lot of it is true, and we believe strongly in cloud computing. But looking forward, there are certain challenges we have to go all address. A lot of you in the room hopefully will help us with that. So with cloud computing, we get higher agility. You want capacity on demand, you get them quickly, and actually lower cost. You transfer the cost from being a capital expense to an operational expense. But with cloud computing, there's a new set of dimensions that the applications, the operational model, and the hardware model have to go through to truly reap the benefits of cloud computing. You Dilip touched on some of them on the hardware side. I'll touch you more about the whole stack in a second as well. There are certain elements in how you should build these systems, we believe. We articulate them. We're going to mention to you in a second. And we actually went ahead and built a system using those elements. And they all hinge around those new dimensions of cloud computing with scale-out architecture. But looking forward, there are these issues that we all going to face going forward. First and foremost on our mind has to do with applications. We can take legacy apps and run them in the cloud. We do this today. But to truly gain the benefits of cloud computing, the app has to meet the cloud model. It has to be scale-out, stateless, replicated state, and so forth. And I'll discuss this in a second. Security boundaries change quite a bit with cloud computing. What was behind a firewall completely is now all over the place. What do we do? And lastly, you'll find out that this notion of a hybrid cloud, multiple clouds, be it different vendors, be it on premises and in the public cloud, will become more of a norm. And then you have to worry about how the applications span these boundaries and how security spans these boundaries as well. In a nutshell, you'll find me describing that one size of a cloud will not fit all. We need to have a whole spectrum out there. And the application model in particular is an area that we all need to be working on going forward. So let me sort of base all this. Let me tell you more about this stuff in bit more details now. You probably know about this already. Why should we embrace the cloud? It really boils down to agility is a big deal. Guys, this cloud stuff is actually very agile. What would take you today perhaps weeks and months from cutting a PO to buying the machine to wiring them up to installing the OS and so forth can be done literally in minutes. I can show you after this talk if you want to. Literally in minutes, you can be up and running. And all the stuff we think about in terms of seasonal differences and using capacity and spot pricing and the like, they're all actually really doable and possible today with the cloud. So agility is actually real. Translating CapEx to OpEx is actually something that they also get with the cloud. Many customers actually would like a hybrid. They don't want a purely operational-oriented type of model. But you can run your business based purely on what you're using, not how much capital you're going to put in the system. And of course, the cloud is, from a networking aspect, very much something you can use as a communication hub, where you put applications almost anywhere and access them everywhere. But key to all of this thing is high scale. We touched on this thing in the Q&A moments ago, how small a cloud it should be as a cloud. Guys, if you don't have high scale and high sharing, you cannot get these properties. How can I give you agility? Well, if you want 1,000 VMs tomorrow, I'll give it to you just like that, if I'm not effectively oversubscribing and having a large clouds available to my disposal at the moment. So scale really what makes it actually happen. But with scale comes issues with security. I'll be running multiple customers. I'll be running Coke and Pepsi in the same cluster. Many issues with sharing the same infrastructure, multi-tenancy issues come to the fore. So remember scale, guys. Without scale, this whole thing is so silly, to be honest. With scale, it becomes real, but you have to solve issues with scale. I want to be very clear how we think of cloud computing. We do not believe that virtualization is equal to cloud computing. Virtualization is an enablement to cloud computing. It's perhaps a necessary function, but by no means is it the only thing you need. To us, cloud computing really hinges on 3 dimensions. One is the application model. An application model that's actually a scale-out architectural model, where an app scales out by asking for more resources horizontally, if you will, not vertically, where the state is replicated. In these systems, a machine, virtual or physical, can go up in flame anytime, any point of time. There's nothing sacred about the machine. Actually, at any point of time when we are running, there's a small number of machines that are literally down. We fix them once a week, as Dilip touched on them, which means the application itself has to be able to handle these failures as well. So the app model is a big deal, guys. I mean, that's something we need more of the apps to move that way. Service-oriented architecture, scale-out architectures are very much on the way there, but they're actually hard to program, especially at the data tier. So how can we make it easy for people to program these highly scalable systems that can be very resilient, that can meet the cloud model is a big question going forward. Underneath that, we discussed quite a bit about the hardware model. The big point about this is, other than it being scaled out and so forth, it's really a fixed hardware model. Some of us are used to designing an application, ordering the machines to match the need of the application, and you have a very highly automized system. Guess what, with the cloud? You have no idea how the hardware really looks like. You don't, nor should you. Yeah, and your app should not care that much about the topology of the actual hardware underneath it. For me to be able to have the scale I need to buy them through the Leaps organization by rack and stacking a lot of machines. The topology is fixed as far as the application is concerned. So the application cannot assume that the hardware can be changed for it. On the other way, on the contrary, actually. The hardware is fixed. It can be a different location, on premises, on the provider, public, and so forth. But it has to basically be able to use whatever the system gives it. Lastly, the operational model, and I think for us in this room, it's not less of an issue, but for many, it touches on something interesting, which is the segment of the market assumes that they can walk to the physical machine and say, this is my machine, and my IT people can go manage it. And we go tell them, no. Going forward, you should manage your application. Forget about the plumbing. Leave the plumbing to the plumbers. That's a value prop for many people, but for some, actually, it's a bit of this, it's the notion of not knowing where my things are, and my people have to learn something different is different, So ultimately, with the cloud model, the shift is from managing plumbing and OS patching and wiring and what have you to managing the application and upward. So that shift of mentality is very important, and it also implies a bit of loss of control. When we started looking at this whole cloud stuff, we looked at all these dimensions, and we realized that there are certain architecture elements that we should build a platform using. And the list behind me approximately touches on everything we thought of at the beginning. One is we very much want a very efficient compute fabric, and for that, virtualization is key. So virtualization is very important, guys. We have to virtualize the compute nodes and the network, such that you can lay almost any graph of computation over a system like that. Each node in such system you have to view it as a cache. It's a cache of data, cache of state in general, software, but it can go up in flame at any point of time. This is unlike traditional computing, where you have a mainframe or a big SMP box, and 3 administrators just watching it every minute. And you have SANs and RAID, and you don't need all this stuff. A machine is actually a cache. It can go up in flames. Somebody else will take over. That's a principle you have to stick with. Otherwise, it's a slippery slope to traditional systems. You have to automate things. The scale that Dilip alluded to is what we operate on. If I tell you how many people I have in my operations team to manage the system, you'll be very surprised, given the size of the systems. It's mostly done by software. And therefore, you have to automate. To automate, you have to understand what the app needs of the hardware. So you have to model enough of the application so for automation to work. The automation need not understand the business logic or what the programming language is or any of the stuff. It doesn't really matter. The automation has to understand the topology of the service, its resource requirements, and so forth. So modeling the topology is very important as well. And for that, you have to have an application model. You have to tell the programmer how to think about it. This is the topology, so what the state is, and so forth. And finally, you have to provide enough services so programmers worry about their code, not about building all the plumbing from themselves. This includes storage services, for example, metering, billing, and so forth. So based on these principles, we went ahead and built a platform. This is Windows Azure, guys. We have been working on this in 2006. It's available today in commercial release, available now, has been since February. I can spend a day talking this one slide. I won't. Very briefly, this is a large-scale public cloud available today. We are hosted in 6 data centers in the Leaps organization. Plus, we have 3 dozen CDN nodes also integrated with the system. The base platform, think of it as an OS in the cloud. It's language agnostic. Use your favorite language, your favorite programming tool. All I care about is tell me the topology of your service, what you need from me. The rest is automated. You get from the platform a number of a la carte services. These are all mix and match. pay as you go for all of them. From basic automation for your service, storage, very large scale storage, to relational database service. You ask for a table or a database, you get it. You don't have to hire a DBA. All the way to a bunch of connectivity solutions, which you may need to connect legacy on-premises software with the cloud as well. And as I mentioned, there's a number of programming tools on top that you can program as you see fit. We are all over the globe today. We have replication of data between data centers. Typically, you have a policy. You decide where your computation resides, where your data resides. It should be co-located or not, and so forth. And you would care about some of these boundaries for geopolitical reasons, by the way. Sometimes you have to be a certain location versus the other, and so forth. How you get to this platform? You can do it now if you wanted to. You can do it from a simple portal all the way to a bunch of RESTful APIs and commands and so forth. Or you can fire up your favorite programming tool, Visual Studio or Eclipse, your favorite programming languages, and you go from there. It looks very much like a traditional system, but with the properties I mentioned earlier. It's a scale-out architecture, I guess. OK. So all this nice and dandy. I'm very proud of all the stuff. We have lots of customers using it. Let's look forward for now for a second. To truly gain these benefits of the system, the certain challenges we have still not totally, as an industry, have conquered yet. One is the application model, which I'll spend a few slides on. The one-liner there is, our forklift approach, where you take your stuff as is and put them in the cloud, doesn't really work. Yes, you can do it with a bunch of VMs and see if it works and whatever. But to really gain out a scale-out model, to get all this resiliency, you have to do something to the application. In these systems, you have a highly shared environment. There's a class of apps out there that the idea of them sharing the same infrastructure with somebody else is really a very strange notion. And also, the idea that you could be hosted somewhere, maybe in a data center in Quincy, San Antonio, or a different continent, is also a very strange thing, if you will. So there's certain security issues and the way we operate this system that we have to go address, and I'll touch on them in a second. And again, the one-liner there is the security issues don't go away. The stuff we have to worry about of where the boundaries are and the like still apply to the cloud. And finally, I'll touch on this in a second as well, you'll find out that for a number of these reasons, a number of the security and compliance reasons, we're going to end up with hybrid clouds. Clouds that exist in multiple places, multiple providers, or on-premises and some provider as well. And an app will have to span these boundaries. And once you have those boundary-spanning applications, you have to worry about the boundaries as well. So let me go through them very quickly. Let's talk about moving an app to the cloud. So you have a cloud provider like us or Amazon or your favorite cloud provider, and you have an application. You want to move it to the cloud. Okay? Well, there's many easy cases. Okay? You have a website. If you can lift the whole website as is and have a front end and a back end and a simple database, you can probably do it. We have customers who have done that. I can tell you, for example, Kelly Blue Book. If you go to Kelly Blue Book right now, you may be hitting their site on premises, or you could be hitting it in our system. I actually don't know. They send the traffic here and there. Their website is mostly read-only. So basically, it goes here and there. It's all nice and dandy. However, there are many other examples where, even for a website, you cannot lift the whole thing and put them in the cloud. You have to divide it through some other cut. Maybe your data has to live in one place, but not in a different country, for example. Or your data is highly transactional, and they have other applications for latency purposes, have to live somewhere else. What do you do? You'll find that there's a bunch of issues you have to look at. And the big point I want to get across is that careful decomposition will be needed for legacy apps. And even for newer apps, unless they live totally in isolation, you have to make them somehow fit with whatever you have. And some of the issues we deal with are this. If today somebody told you, or your IT department, move stuff to the cloud, you'll find yourself asking these questions. There's actually a bit more than those. So let me go through them, just give you a flavor of what I'm talking about here. Data is usually the biggest question. Where is the application data? In a scale-out system like these cloud systems, data have to be replicated. And it has to live in the network. So your app can be sophisticated. and you do your own replication, nice and dandy, or you have to find a store somewhere which is highly resilient for you. So making sure that data is replicated in somewhere on the network is the most important part. As I mentioned, guys, every machine is a cache. So you cannot assume any single spot is golden. Related are config settings for your application set. And how do you install it, and boring stuff like that. You may not actually care about this, but actually when push comes to shove, you have to make sure that any configuration for the service is also obtainable from the network or can be obtained, if you will, when you start up. Scale, it has to be horizontally scale architecture. This is the hardest one for many, by the way. You cannot assume you can throw more memory at it or ask for more CPUs because there's a limit for any scale-out architecture. Today, we might be at 8 cores or 12 cores, whatever the number is. If your application requires 16 cores, it better be a scale-out, message-based type of architecture. Okay. And for resiliency, you have to have many of those and so forth. Dependencies in general. You may have a self-contained system where all your dependencies are maintained by you. That's nice. In many cases, you have dependencies of somebody else. And how do you connect to them securely and so forth? Latency. Remember, you get what you get from the cloud. So if you have two components and they have to be very, very chatty, you may be able to specify I want to be close to each other. But you can also say it has to be an InfiniBand 10 gig connection. You know? So there's a class of apps you may not be able to move to the cloud today. Just let me jump ahead to the very end, security and regulations. And I have a slide on this one, which is the next one. You find out that the location and the type of the cloud is very, very important, not for technical reasons. All the rest of stuff is technical, data, latency, replication, blah, blah, blah. This one becomes somewhat irrational. This becomes that this country says data must remain within my national boundaries. So you have to make sure that this part of your application stays within your national boundaries, whatever the country may be. Or your data could be subject to compliance. And there's an alphabet soup of compliances out there, from SAS 70 all the way to you name it. And you have to make sure that that part of the computation follows these rules. So how do you go about it? It's a long list of security considerations. Before reading you a slide, which I won't do that, then the thing here is that you could effectively, what you're doing effectively here is you're perhaps outsourcing your computation to somebody else, but these things you don't outsource. These things you have to be concerned with, even if you're running it at a cloud provider. Identity, of course, is a big deal. You will end up most probably with some federation story. You may have local identity system in your organization, and you want to make sure that scenarios such as single logon work. So when your application, which is running in the cloud, can carry your identity with you. So you have to have a federation story with that as well. We have technology for that, but in general, you could have to federate with OpenID, LiveID, AD, etc. So how do you do all these things? The operational processes of classical IT have to be changed when some of those applications are beyond their boundaries. So you may still have to follow some process of a SAS 70 or ITAR, or whatever the case may be, but they have to extend, project from your local IT all the way to the cloud as well. Today we think that by having a firewall and stuff behind the firewall, we're fine. Okay, many people think this way, to be honest. Here, the communication endpoints for these services end up being all over the place. Your app, your service is multiple places. There's no firewall per se. You can put rules and the like, but there are no firewall per se. So how do I get my hand over understanding what's going on? How do I log everything and get the right order trades and so forth? And that requires a shift. And this, to be honest, mostly an IT discussion. And it can be a difficult discussion. But it's needed if this stuff has to really take off. Then there are the very difficult one of regulations and national boundaries questions. For a class of apps, this does not matter. For many others, you really have to answer the first question. Do you really know where data is? Do you know that your infrastructure, your provider, is replicating your data around? Do you know where the packets are actually flowing? Are they crossing national boundaries, or if so, do you care or not? And again, for a class of workloads, this becomes a very sensitive question. So you have to understand, you have enough visibility when you put your data somewhere that it's being replicated in a certain way, it's going to certain places but not other places. And frankly, even in infrastructure we have, all the way from the GFS infrastructure all the way up, we have certain guarantees of the network topology and our own providers we depend on to understand where the data is going and not going. These are very important questions, actually. In general, you'll find out that these platforms will have to add more policy controls along things like location, access control, audits. Those sound kind of boring, guys, but once we sort of replicate these things, they become harder and harder to actually put together and bring them back, to tie them back to on-premises policy systems. So the usual answer, and this is what we do in the industry, is to say, great, we believe that we will have to deal with these boundaries. We will have to put computation in different places, perhaps on premises, perhaps in a public provider, perhaps some in one country versus the other, which quickly leads us to a picture like this. End up with hybrid clouds. This is a fancy word for saying you have multiple data centers on different places, perhaps controlled by different people. And with this, you end up with interesting issues to deal with. Let me just give you a flavor of the tension you have in here, why you care about these things. Look at the usage pattern for a cloud. They range from anybody can use them. Windows Azure is an example of that. Amazon EC2 is an example of that, AWS, where it's a public cloud available to everybody. Get your credit card out, anybody can use it. Okay? High scale, all the properties I discussed apply there. Okay? But you have less control over where things are happening. All the way down, you can envision very much hosted cloud for you, for your exclusive use. You come to me, I'll give you your own cloud. So you have lots of properties, okay, but they're nonetheless they sort of hosted as somebody else. The other dimension has to do with really honest God control and location. Traditional systems really are way out here. They're on premises. They're behind your firewall, your physical building, under your control. However, they tend to be much smaller. The few of us have the scale to warrant building very huge clouds. So sometimes people end up in somewhere else in the scale where they try to host them somewhere else but gain the control. And this tension, the pros and cons are all over the place here. We believe, by the way, no one end will win. We today have a very large public cloud. And as the gentleman that alluded to, we're also going to provide so others can host it or you can do it on premises too. We believe it's a fact of life that we're going to have all these three locations. But once you do that, you have to worry about, as I mentioned, crossing these boundaries, security between them, data synchronization between them. So the conclusion here is that one size of a cloud doesn't fit all. Those who would advocate that private clouds, I'll do it all myself, I don't think this really makes sense. And purely a public model doesn't make sense neither. And there are trade-offs here, and then it boils down to the application itself and its component, how do we target to the right place. We believe that these things will evolve, to be honest. Today, public cloud stuff really very much in people's minds means virtualization. And they're really evolving to be more like what I'm discussing right now. And we are basically doing it by giving them the public cloud on premises. We also believe the public ones will segment more. There will be segments per industry, healthcare, retail, et cetera, that you can take what you think of as a public cloud and make them more aimed at a given market. But to make all this happen, we have to collectively invest in connecting these universes. Some of this is not rocket science, to be honest, but there's actually work to be done here between what you can think of stuff running in the cloud and stuff running on premises. And the stuff running on premises could be a cloud model, could be classical model as well. And they range from secure network connectivity, think of network overlays, VPN technology and steroids, if you will, through a federation of identity and access control. Application connectivity, you want to be able to connect your parts of your application through firewalls and what have you, all the way to data synchronization, because you will end up having to build these building blocks to make your application actually happen. By the way, in our product portfolio, we have technologies in most of these buckets, either announced or we are working on it as we speak. These are needed to actually get the model I told you about, the hybrid cloud model to actually work. So put it all together, looking forward, we believe that the application model will actually become the default. Everything else we believe will become legacy. We do believe that applications will evolve to a scale-out model where data is stored elsewhere, where resiliency is really the basic model how you build these systems. Meanwhile, we and everybody else in the industry has to bring legacy along, have virtualization techniques to bring the old stuff with us to the cloud and the like. But the new cloud model has to become the default. Otherwise, these true benefits will not actually happen. We also believe that public clouds will become more mature. Not just ours, Amazon's and others. We are going to become more mature. But having said that, the other parts of the spectrum I mentioned will continue to exist, mainly because of regulation, national boundary issues, and sometimes businesses trust their stuff when they're closer to each other. At the same time, specialization of the clouds, we see it happening. It could be the same technology, same data center, same container, same software perhaps. The policy, however, the control over a certain cloud will become more specialized and sold differently, per segment, per market, per country even. And the big one is handling both security and management, including policy controls, over these boundaries. Because if you believe the story I told you, you're going to have multiple of these and multiple boundaries, how do you deal with everything across these boundaries? That's going to be something we really have to go deal with. And policy run, if you will, job management and application management is something that will be needed. If you look at the startup space, by the way, there's a bunch of companies working on just like this space. At first glance, look at them, it's like, what are they doing? But they're realizing they have to broker effective services among multiple locations. So guys, in conclusion, and this will leave for 5 minutes for questions, we believe cloud computing is still very early. We've been working on it for a number of years. We love it. We're investing billions in it. I'm looking at Dilip here. But it's still very early and very exciting, to be honest. Having said that, there are certain things that we have to all work on. One size will not fit all. I think a complete spectrum from on-premises to third parties to public clouds, segmented by different workloads will actually happen. And the big thing in my mind, at least, the application model has to evolve. It has to become easy to write easy applications, which are scalable and so forth. And if somebody wants to do the rocket science and build the next Facebook, they should be able to do it as well. OK, guys, I'm done. I have 5 minutes for questions.
Questions. First hand up.
Hi, that was great. Do you think that third-party licensed vendors of applications get this?
Third-party applications. Actually, the question is about third-party applications.
Correct, yeah. I mean, those who sell licenses in a very traditional model today, do they get this?
There's at least one vendor I can think of that doesn't get it yet. I won't mention names. I can tell you that a lot of companies, especially medium ISVs and even some big ISVs, are looking at the cloud and saying they want to shift their portfolio of applications from being standalone, licensed through normal means to software as a service applications. And they're asking platform vendors like us to provide them all the plumbing, including the services they need, like billing, for example, and how to monetize a software. So more than I expected, perhaps, at this stage, yes, they are very much all running toward that. I can tell you that collectively, we haven't told them exactly how to do it yet. There are a lot of things to be done to do multi-tenant applications and figure the monetization model with it as well. And with that, by the way, licensing will be quite different. We'll be very much more of a billing, sort of metering type of usage model. Some vendors don't get it quite there, but I think they will soon. Up to you. Dennis, up to you.
Okay, I have 2 questions. First is, we know that this, except the Azure cloud platform, there's also others like Amazon, and a lot of people, in fact, has been getting hands-on that. But if the users, they want to transfer, let's say, from Amazon to Azure platform, what kind of interoperability we have from an architecture point of view? And another question I have is, as you showed that some organizations, they may want to have their own closed private cloud. For that spectrum of users, do you plan to sell the Azure platform, the software suite, like Windows operating system?
Let me answer the second one first. We just announced yesterday, literally yesterday, that you will be able, as a customer, to buy Windows Azure as an appliance. Appliance is what we use basically as a complete package from OEMs, hardware, software, and networking. So we announced this thing only yesterday. I can give you the information about this. But basically, every functionality I mentioned to you, you'll be able to buy it in due course and deploy it locally in the data center with a minimum size to be determined. And the model you're going to go through hardware OEMs. So it will not be sold like classical Windows Server where you buy the DVD and you put it together. Instead, you'll buy it as a package from the OEMs with different configurations and the like. For the first question, the interop question, everything I said today, everything, all the management APIs, all the storage APIs, etc., are documented. They're actually RESTful APIs. We have different language bindings to them, very much with an eye toward people can go back and forth. I can tell you I have customers today who are using my platform, using Amazon, for example, for storage or vice versa. Beyond that, there are no standards yet at this space, but at least the building blocks are all very much documented through standard protocols here. There's no lock-in that way.
So question about more on the implementation side. So let's say I'm a customer and I want a maximum of 100 nodes.
Yes.
Can you tell me about what kind of failure domain guarantees you can give me? Basically, can you say, we won't put any 2 nodes on the same processor, we won't put any 2 nodes in the same container, on the same backend, power supply, et cetera?
Question was failure domains and how. So remember I told you we modeled that topology of the application? There's actually something called failure domain specification. It's called failure domain. You specify things like failure domains. You specify update domains as well. And you specify size and a few other things as well. We take this information and we compute the most optimal configuration and we lay over your application over the physical topology based on that. And the guarantees we give you is a failure domain is basically what we view as a single point of failure. And today we map it to an actual rack. Okay? We don't document it, but it's actually rack. An update domain is something that we will use when we sequence through a rolling upgrade forward or backward at a time, because you want to do n plus 1 and so forth. And we make sure that in such a way that if there's a failure happening, you will not, during the rolling upgrades, you will not lose availability. Okay, and I can tell you offline more about that. That was a part of the foundation here.
Just on that interoperability question, I guess it's quite difficult now to deploy an application across.
I can see you guys. Sorry.
So I'm over here.
Oh, yeah, sorry.
So I guess because of the different characteristics of Amazon and Google and your Azure cloud, it's quite difficult to deploy the same application on 3 different providers. But going forwards, do you see a pricing market where I would actually deploy across Amazon, Google, and Microsoft, and that at runtime the user would choose based on price? Do you think there'll be a market for compute and storage?
Short answer is yes, but let me first address the first part of your question. It is true that the more you move up the stack, which is the case for Google App Engine today, the more you are in a sort of different space, if you will. We're actually, in a sense, between us and Amazon, we are more of a platform as a service than infrastructure as a service, even though you will be able to run also virtual machines on my platform as well if you want to, by the way. So the portability question either will be solved or we're going to get there. But to get to the core of the question, I do believe there will be, that's why all these startups are trying to do the same thing, by the way, broker services and ability to go decide for certain functionality, can I go here or there? And the respective providers have to differentiate through some other means. Maybe ease of programming, SLAs, etc. There's a question how much of a commodity play it will become, to be honest. And if you look at our platform, we are shying away. We shied away from day one from giving you just a bunch of VMs to go by yourself. This business automation, failure domains, and other domains is actually part of the platform. It's not an optional service, like, for example, this one in Amazon. So this is the fundamental stuff we believe that platform should provide, and we will differentiate that way. But ultimately, some aspects, yes, you'll have options to go here or there. especially for, say, unstructured data, for example.
Amit Sheth, Wright State University. Just a little advertisement. We work on Cirrocumulus, which is to allow you to design a software such that you can deploy in multiple or different cloud of your choice. So people are building libraries or techniques to do that. Yep. My question for you is along the federation issue. I think it might be quite attractive, and I think you generally covered that, but I have some more detailed questions about people having their own private cloud or small cloud of which is their regular needs, and then rather than building out for peak needs, then use the public cloud, on those spurts or when those needs are. So that way, I think you can use your if you have totally high utilization of your equipment, that may come out cheap anyway. What do you see in terms of the software and its availability and the techniques for people to be able to quickly do that? Do you see, without necessarily any promise from Azure, having such software? Now, if you do it from, if I actually have installed Azure software on my own thing, perhaps it might be easier to, because I'm going to the same public cloud infrastructure. But generally, any ideas along that line?
Short answer to your question is that people are already doing it today.
Okay.
I can tell you from my own customers, are doing it today, such that they are using the cloud, our cloud at least, as a way for bursting for easy extra capacity. Now, to double click on, I know where you're coming from. To double click on where you come with what you move and so forth. It depends very much on the workload and which part of the computation you want to burst. I mean, I gave you an example of a single customer that actually replicated the whole site as is. Okay. Others take a part of their workloads. In this case, some customer I know of that does basically embarrassing parallel application. And that part of the computation runs to the cloud. The coordinator key is kept on premises. A different customer using data synchronization. So they synchronize the data to a cloud-like layer and runs in the cloud. So there's a whole spectrum of people running the same exact thing to dividing part of the service and saying this part I'm going to be able to burst in the cloud. It's a deeper discussion. We can discuss offline more as well.
Okay, I'll do.
I think we have time maybe for one more. Yes.
Yeah, thank you, Dennis. Joseph, HPC.
Yes.
So Microsoft entered HPC quite a few years ago, more aggressively, and I see a couple of experts in the cloud group coming from HPC. Do you need a special environment or a substructure to prepare for HPC services?
So, as you know, the whole HPC is a big spectrum here, yes, right? So there's a certain class of application we call HPC today that amazingly suitable for this cloud as it is today. I mentioned embarrassing parallel applications, for example, and we have a documented case study, for example, a company called Risk Metrics. They do risk analysis for Wall Street. And again, this stuff is public information. They actually use us today for that class of applications very easily. Okay. There are, however, as you know, a class of HPC applications that are far more latency sensitive, for which you want to have MPI over InfiniBand and so forth. I think you'll find that your classical public clouds will not be suitable for this anytime soon. However, there are opportunities for segmented or vertical clouds, which is what I mentioned in the previous slide. I believe there will be a market evolving where perhaps for a smaller market but more specialized market, the same architectures will evolve to meet their needs. But there will always be tension between a very public, huge scale cloud provider, which is cheap and agile and blah, blah, and more specialized needs. And if you, on the spectrum of HPC applications, some of the specialized needs I think will only be served by more specialized providers, whereas the rest will gravitate to the public one. That's it.
Okay, I want to stop at this point and thank Joseph and Talib very much for these presentations.